correction from what I said last time. So last time I asserted the following facts, that if so there was this statement that if pi is a supercuspidal representation of say a semi-simple group over a local field, which is n chi distinguished, then one can find a matrix coefficient f. So matrix coefficient of pi. In other words, a function of the following form for some w check in pi check, the contragradient. Okay, so any function of this form is a matrix coefficient. So we can find a matrix coefficient such that the integral is not zero. So I think last time I had such a statement, and in fact in my construction of Poincare series, I'm trying to globalize some bunch of supercuspidal representations. At those places, I take a matrix coefficient of this type. Okay. So, and then I proceed to give a sketch of a proof for the why you can find such a thing. But I think that proof is kind of bogus. So I'm going to redo it briefly. Okay, so here's how you should do it. So since this is not zero, so you can choose some, so the proof of this assertion, you choose some non-zero L in this Hom space. It's not zero, you can choose it. Now, so L is in particular a non-zero linear functional on pi. Okay, so for any, so let's say you fix some, say W naught in pi, non-zero vector. Okay, then, of course, since this representation is irreducible, pi from this W naught, you can get all of pi if you use the action of the Hacker algebra, or basically all the completely supported locally constant functions. Okay, so so there exists f in here, such that L. Oh yeah. By the way, what is this this action here? Maybe I recall that first. So the action here is that if you have f in here, then f of W naught is defined in this way. Okay. Okay. So since L is non-zero, so there exists f such that L of f W naught is not zero. Okay. But of course, if you write down the definition, okay, if you apply L to it, so this integral is actually just a finite sum because you have completely supported locally constant function. So since it's a finite sum, you can exchange this linear functional with this integral sign. Okay, you can bring it in, and then you see that this thing is nothing but let me see, is fh L of IHW naught. Right. Now, of course, you can just continuing here. Do it here. So what I want to do next is, I guess I want to break this integral into two parts. I break it into two parts. So since this is not zero, the inner thing is also not 0. Okay? But let me write down what the two parts are. Okay, so we have 0 not equals to L f w naught, which is equal to integral n mod h integral n. So of course you will have this, and you will have this. Okay, but this linear function has the property that it transforms by chi, right? So this guy is chi n L I h w naught. Right. So okay. So anyhow, you're going to get this dot so in other words, since this is not 0, this is non-zero for some h, right? Because this is a function of h, and if it is identically 0 for any h, then this is. So I produce a function. I mean, it kind of looks like what I want, but I want to show that my function must be of this form. Okay. Now, why must this f be of this form? Well, the reason is so why is f? Why must such an f be a matrix coefficient of pi? Okay. The reason is because the map that sends f to pi f is so it's a linear map from here to endomorphism of the vector space under pi. Right? But in fact, it is maybe a smooth endomorphism. So this space is since pi is supercuspidal, and in fact, one knows that this is the maximal pi check tensor pi isotypic quotient of this thing. But since it is supercuspidal, in fact, it is also a sub. Okay? So, okay, so I guess because it is supercuspidal, since pi is supercuspidal, this function, in fact, this quotient splits. I mean, you can embed this pi check back. So, yeah, so it splits. Okay, and what is this splitting given by? Basically, I want to say the embedding can be given by. So this is so let me write something here. Okay, so this is basically realized by formation of matrix coefficients. And this part, or subquotients, okay, in other words, it has nothing to do with that. Okay, it has no subquotients isomorphic to pi check.
Do you assume that the center of H is compact?
Yeah, I assume semi-simple. Last time when I talk about the proof, I just say let's just work with semi-simple. So yes, okay. So I have okay. So this means that you see this guy has nothing to do with pi check. So under this map, right, this map f to pi f will Q this part. Okay. So I start with any f. I have found an f such that this thing is not 0, right? But this f, you can write as two components. This component will always be Q under the map f going to pi f. So without loss of generality, I can assume f lies in here. Okay, so without loss of generality, our f is of the form it's a matrix coefficient. Okay, so this is a technical point. Why don't I put an h here? Why do I put an h there? Because integrate, do this integral, I have to put the h here for it to be non-zero. Okay? So the upshot is my f can be taken to be this form. So this means that this integral is not zero, right? I n h n for some h. Now, of course, I simply just use just another vector in pi check. Right? I just call this w prime check. Let's say. Okay. So again, this is not zero. So if I bring this n to the other side, I will have an n inverse. I change variable. I replace n by u inverse. Let's say. Then I will get chi u inverse, and, which is what I want. So this is okay. Okay. So anyhow, sorry for the long correction. At the end of last time, I stated also a lemma about globalizing the central character. So I said I won't prove it, but now I changed my mind. I decided I want to prove it. Okay, so let me restate the lemma. So this lemma is for globalizing central character. Okay. So this is when I was proving the corollary. Okay, I have a theorem, right? And I have a corollary, and in the corollary, I only have local data. Everything is local, and then I have to start to globalize the field, the groups, all kind of characters. And one of the data I would need to globalize is a so-called central character. Okay, so the setting is so K is a global field, characteristic P. Okay. Then I have Z is a connected K torus. Yeah, and it's such that with K of V naught is some F. I have a K torus such that the F rank of so this is such that, so let me say V naught is some fixed guy, okay, that I'm given. So the F rank of ZF is equal to the K rank of Z. In other words, for example, if this is GM, this will also be GM, as opposed to some anisotropic torus. So given, say, unitary character, claim is that there exists a global automorphic character of this torus, such that, so of course you want the place of V naught to be the given omega F. Yes, okay. And what about at the other places? Okay, so just like our globalization theorem, we can get very strong control. So we want omega to be trivial on a subgroup of this type. So this is some non-empty finite set of places. I'll explain what this one is. Disjoint from T naught, from V naught. If V naught, you already know what is happening. So here, the zero refers to, I'm looking at the maximal bounded subgroup, maximal compact of this torus. Looking at maximal compact. This one refers to the, I'm looking at the maximal pro P subgroup of the maximal compact of the compact. I can also look at the maximal compact at these places, but I want to take some groups smaller. Okay, so that's the lemma. so you can see that this character is this automorphic character. It's it's unramified outside of this set, but I need to have at least one place here where it is slightly ramified. Slightly ramified. The ramification is tame here because it's trivial on the maximum rho p. Okay, so I want to discuss the proof of this. Okay, it's actually this. I think these are things probably well known, but it was not obvious to me. But the proof we are going to present is largely in a paper of Dipendra Prasad. He wrote it in the number field case, but you will see those. Okay, so let me just say. Okay. So let's consider the map I from this group. We better give this group a name. Let's call this this. Now, so what do I want to? I mean, this is a natural map, right? And because this is a compact group, right? So this is compact. So the image here it has so the image of I is closed. It's a closed subgroup, okay? Because the image will also be compact. Okay. Now, okay, so the claim is that the kernel of I is trivial. Let's see how this implies the lemma. Okay, let's assume this for a moment. Assuming claim. Okay, so this is an injection. So the image is a closed subgroup, and by I guess the theory of representation of locally compact abelian groups, so Poincare, the theory of Poincare duality, and so on. If you give me a closed subgroup of a locally compact abelian group, you give me any character on that closed subgroup, unitary characters, it can be extended. Okay. Now I'm looking for characters of ZA mod ZK, right? I'm looking at a character of this, which is trivial on this thing. Okay, so I can find it. Okay. Now, actually, sorry, I wanted to say not just omega, but let's say omega cross, because omega is missing one place, right? Which is the place at V0. Okay, I want to put this thing in there. It's still compact, okay? Because omega is the product of things outside of V0. So I just add it in. So the claim is that by I guess Poincare theory, say you can find a unitary character such that omega is trivial, and the restriction to zk v0 naught is equal to omega f restricted to . So now this character is almost what we want. Firstly, it's by construction trivial on the omega, and then okay, so and it almost agrees with what we want. Right? It agrees on the maximum compact. Okay, sorry. Okay. So we have to adjust it a bit, but now we haven't used this condition that the F rank and K rank are the same. Do it on top. see, okay, so, I mean, this Z torus, okay, so it has some K rank, let's say M. So this means that the maximal split torus inside Z has dimension M. Okay. So this means that we can find a quotient to, maybe I should call it R, okay, so let's say R is equals to the K rank of Z, which is the F rank of ZF. Okay. So you have a map such that the kernel of Q is, well, it's a torus, okay, and it's anisotropic over K, but because of this condition, it is anisotropic over K V naught, and hence over K. So it's a torus over K, which is compact at V naught. So it's compact over K as well. All right, then, so our character, let's look at this character. Okay, so this is a local character, right? It's a character on Z K V naught. S1 is, it will factors through because the kernel is some compact group, and we have already agreed, these two guys agree on the maximal compact of this. Okay? So it will certainly factor through Q, okay, which will project to K V naught cross R copies, and then if you apply the valuation at V naught, you can get to Z, let's say. I mean, that is firstly such a map, right? You apply Q, then you apply the valuation. Okay. Now this map may not be surjective, but it has a finite co-kernel. Okay. But more importantly, the kernel of this composite is compact. Okay, because from here to here, the fibers are compact, and here to here as well. Okay. So, which is this composite has compact kernel and whose image is has finite co-kernel, okay, and has image finite index. Okay, so, right, so because the kernel is compact, so, and I know this is trivial, the maximal compact, so it will factor through this map. Okay? And of course, it's not it may not be trivial, but now it is clear that we can, so by twisting, multiplying to omega prime, character of the form yeah, so Q composed with product over I equals to 1 to R, just some absolute value map like that. We can make omega prime V naught equals to omega F. Because you already know that they agree on a maximum compact, and so the quotient factors through this. I just use something like that. This is an automorphic character of this composite that is automorphic character of Z. Then I can account for the difference at so that and the proof assuming the claim. proof of the claim. Okay, so let's okay, so let Z over K be a splitting field. K or just K. Of Z. This is a separable extension. Torides are split over a separable extension. So so ZK will sit inside ZE, and since it is split, so I choose some isomorphism to something like that. Okay, so the upshot is any element. So if you have a Z here, okay, I just think of it as its coordinates, okay, which are elements of E. Now, of course, E. Note that E over here. E is the function field of some curve Y. Okay? And this Y maps down, Y tilde, sorry, maps down to our curve Y. Okay? Meaning, yeah, so if this K is a function field of some curve Y, it need not be the same residue field. This is my K. Okay, then such a function field is correspond to a curve, right? Okay, so so now suppose my Z lies in the kernel. Okay, so if it lies inside the kernel of I, in other words, it is kernel of I is just ZK intersect this, right? Okay, so what do we know? Well, so this thing is contained in the maximal compact, right, of ZA. So if so its image, okay, under, what do I say? Okay, so if Z lies inside here, okay, its image in here will live inside the maximal compact of this, okay, which is the product of the units. Right? So this means that these are elements in E, right? So they are functions on this Y tilde. They will have no poles and they are regular. They have no poles and no anywhere because they are all in the units. Okay? So they have no poles. So they must be just constant function on this curve because they are rational function on Y tilde. And since they are in the units they are at every place, place of E. If you think in terms of functions, it means that these functions of Y tilde have no poles anywhere on Y tilde. That means they are constant functions because this is a smooth projective curve. Okay? And now, however, in omega, if you recall, you have this part, right, which is a pro-P group. So if my Z were in this intersection, that means that at some place of E, it will live inside the maximal pro-P of this guy, of the maximal compact. Okay? And the maximal pro-P is just those units which are congruent to 1 modulo the uniformizer. Okay? So this shows that for each of these functions, they are equal to 1 at some point on the curve. Okay? So we know they are constants, and they are equal to 1 somewhere, so they are equal to 1. And so if you are in this intersection, all these coordinates are 1, so the intersection is trivial. Okay? So let me write this down. So, okay, so let's say at all points x in Y tilde, close points, this Zi is regular, okay, holomorphic there. Okay? So this implies that the Zi as functions, are constants. Okay, since T is non-empty, at some okay, so this implies that Zi is equal to 1 for I. The reason is because then Zi must, at that Zi of X will live inside, since Zi of Zi is congruent to 1 modulo if X lies above a point or a place in T. Okay, anyhow, that's the argument. So, now, I want to give this argument because you see, there is no reason right. So over here we are trying to construct omega prime, so it's trivial on omega. So I impose this. Here I know what I want. Okay. Yes, but you see, well, this argument is quite flexible. I mean, for example, suppose I can in the set in omega, right? So I have those set of places in T. I don't have to take the trivial character. I can take some highly ramified character on this guy. Okay, I can do that. Okay, I take a character which is non-trivial, which is highly sort of ramified. Okay, the conductor is very big. Then, so then I could, instead of saying this equal to 1, I would replace this 1 by the relevant character that I'm. Okay. Then I would. Can I rerun this argument? I think I can rerun this argument. Okay, because this part is just about V0. V0 doesn't change. I still impose the same way. Vectors through all this. Okay. Then when I twist this, of course, I produce a character that does this. But how about at the places in T where I have this highly ramified character? Well, because this is an unramified twist, it's not going to change the fact that at those places in T, I'm not going to change the conductor of those characters because I'm just doing unramified twists. Okay? So what I want to say was that you can have a variant of this where at the places in T, you put some character or large conductor, anyone you like, okay? And then it's basically any character you like, and you will produce this omega prime that globalize your omega F, but at the places in T, you didn't change the conductors. Okay? You can maintain a highly ramified nature of those characters. I'm going to use this, that's why I mention it here. Okay. All right, so this is to clean up some things from last time. So what I want to do today is talk about some applications of this globalization theorem that I talked about, whose proof I discussed last time. Okay, so in fact, the main reason why we proved this, the chief application, the main application, is actually to complete the Langlands-Shahidi theory. In characteristic P. Okay. So I'm going to sorry, just to explain what this theory is about. Yeah, so just background information. Okay. Now, whatever this theory is, you want it over number fields and global function fields. But for number field, it was due to Shahidi. And he did it almost 25 years ago, around 1990, early 90s. Okay. But the characteristic P version was not fully developed. Okay. And however, with the globalization theorem that we discussed, it has now been completed. Okay. And this is the work of my co-author, Luis Lomeli. In fact, that was what he has been working on since his thesis with Shahidi. So let me say what this Langland-Shahidi theory is about. So the setting is like this. So you have some connected reductive group G. It has a parabolic. To fix ideas, let's assume it's a maximal parabolic, whose levy is H, because I use H for the group, and whose unipotent radical is N. Okay. So over some global field. Oh no, actually let's do over local field first. Okay, and now you give me pi. Let's say you give me pi, an irreducible representation of H. Okay. Now, because we have this, so we can pass into the dual group, the Langlands dual group. For this motivation, so let me assume the groups are all split, okay? So you will have G check, the Langlands dual group. It will contain a parabolic whose levy is the Langlands dual group of H, okay? And there will be some unipotent radical. Okay? Then you let H check X on the Lie algebra, because H check normalized N check, so there's a corresponding adjoint action. Now, of course, under this adjoint action, you will decompose this into, so these are complex group, by the way. The dual side, I'm working with complex group. So it's going to break up into irreducible pieces. Okay, so let's call this the irreducible decomposition. Okay, so you're going to get a bunch of this. Okay, and on the other hand, if you assume you have local Langlands correspondence, LLC, okay, then pi will give you what is called an L parameter, which is a map from, say, the Vedelin group to the dual group. This part is purely motivational, okay? Just trying to explain what the Langland-Shahidi theory is trying to do. Okay. Well, however, we have this representation, so let me call VI the underlying space, let's say. So I can compose with this guy to GLVI. Okay, so now I will have a certain finite dimensional representation of the Vedelin group. And associated to this, I can define, L factors. So L factors for Ri composed with phi pi. Okay, phi pi is this. Right? Okay, and I can define this local epsilon factor, depending on some additive. So this is a local L factor. Local epsilon factor. So of course, the definition of this is very simple. It's just like the RT-nel function. Okay? But for this, it's non-trivial, I would say. Okay? So this, yeah, maybe it says Langlands, Lin, and in the function field case, Lamont did something. Okay, So we'll have these factors, right? So if we have in this setup, if we have local Langlands correspondence, we will have this. Okay. So the goal of Langland-Shahidi theory, okay, I'm going to call it LS. Okay, LS theory, sort of aims to define these local factors directly, so to speak, without invoking the local Langlands correspondence. In other words, directly from pi without passing to the L parameters or the so-called Galois side. Directly from pi. Okay. So the point is without invoking LLC. That is the goal of this Langland-Shahidi theory. In other words, let me formulate the so i.e. we want to define LS pi Ri, okay, which should be like correspond to this guy under local Langlands correspondence, and we hope to define, which is the analog of the epsilon factor. Okay. Now, okay, this is what we want to. That's what the Langland-Shahidi theory is trying to do. To give a definition of L and epsilon factor on the representation theory side. Okay, and in fact, it suffices to define a, let's say, causal invariant called the gamma factor. Okay. Now, and actually from this, okay, so this is expressible in terms of these two. Okay, so this gamma factor, if you have those two, it is just this times L 1 minus S I check I. So you see, this is a causal invariant because if you know this, if you have those two, you can of course define gamma to be this, and then you will get this this invariant. So it's not a new invariant; it's just dependent on L and epsilon. But conversely, okay, if you have this guy, there's a way of extracting out this L and epsilon. Roughly speaking, let me see. Let's say this guy will be the new. I mean, you will prove that this is some rational function in Q to the minus S, and then so it's basically polynomials over polynomials in Q to the minus S. And these polynomials may not have constant term 1, but you pull out the constant term, okay, so that now the top and bottom are polynomials with constant term 1. And you are going to define the denominator, you're going to define one of these to be the numerator and the other one to be the denominator. Okay? And whatever constant is in front, you define it to be this. Okay? Now, of course, there's something to check here because it's not as if we are defining two independent things. Okay? So there's something to be checked about this gamma before you can do this unpackaging to get the L and epsilon. Okay? But I'm not going to explain how that is done. So let me just say that roughly speaking, this is a rational function, and if you take the numerator or denominator, okay, that will give you the L factor. Okay? And then you pull out the constant terms from the numerator and denominator so that to make the top and bottom have constant term 1, then whatever is out here will be the epsilon factor. And this works precisely as I described if pi were a so-called tempered representation. Okay? And if non-tempered, then there's some standard way of getting it. Okay? So the upshot is that instead of talking about L and epsilon, let me focus on this one. That's what I want to say. Okay. So but let me give a couple of examples. of this setup. Okay, so for example, 1, you take G to be GL M cross N, let's say, and you have a parabolic whose levy is GLM cross GLN. On the doer side, this is still GLM cross GLN. I mean, this parabolic is still just the same one. And then there's this N check. Okay. So in terms of matrices, if you are on the G check, here will be M by M, and here will be N by N. And this part will be your N check portion. Okay. So under the adjoint action, you see that in this example, Li and check as a representation of GLM cross GLN is just the action of GLM cross GLN on M by N matrices by left and right multiplication. Okay, so that is just the so-called standard representation for, let's say, GLM tensor, the standard representation for GLN, just the action on M by N matrices. So according to, and it's irreducible. So this thing is just R1, so to speak. There's only one vector. So according to, so what we hope to do is to define, if you have pi 1 tensor pi 2 in the irreducible representation of GLM cross GLN, you hope to define this gamma factor. And what is this? And so this gamma factor is usually just written like this, okay. And it is basically the ranking suburb. Because on the, if you use the local Langlands correspondence, it's just the tensor product of the two Langlands parameters. So that's one example. Let's look at another example. So now let me take SP2N. Okay. Let me take a parabolic whose levy is GLA cross SP2N minus 2A. The dual group is 2n plus 1c. The dual parabolic is GLAC cross SO 2n minus 2a plus 1c. And then you have n check. What is so on the dual side, so here is your GLA, here is your SO 2n minus 2a plus 1. This part is determined by that, so I don't, right, so if I write A in here, then here is something depending on A. So the unipotent radical, you see that it breaks into two parts. So again, this part is determined by that, so it breaks into two parts, R1 and R2. Okay? So in this case, Li of n check is R1 plus R2. What is R1? Well, under the conjugation action, is basically, so this is, again, this is like A by 2n minus 2a plus 1 matrices, and the action is left and right multiplication. Okay? So R1 is nothing but the standard for A, tensor the standard for this SO, whatever, okay. And R2, this part doesn't do anything to that. So it's these two guys that will act on this. So it is the exterior square of the standard. Okay. So in this case, the Langland-Shahidi theory will attach two gamma factors. Okay, so you are going to get So if you have a representation, pi tensor sigma in GLA cross SP 2n minus 2a, you should get two gamma factors. And this thing is just what people call, I mean, it's just a ranking-Selbert type gamma factor of GL cross a classical group. This other guy, in fact, doesn't depend on sigma at all. So it is what people call exterior square gamma factor. Okay. These are just two examples. So what is the theorem from Langland-Shahidi theory? So the theorem, as I said, this is Shahidi for characteristic 0, and Lomeli characteristic bigger than 0. Okay, it says that for pi, so in the above setting, okay, so but unfortunately they can only deal with so-called generic representations. So this stands for generic representation, those that has a Whittaker model. For any generic representations, so one can define these gamma factors. So I'm putting myself in the same notation as above, okay, in the setting. So I have these gamma factors. And these are rational functions in Q to the minus S. Q is the cardinality of the residual field of F. Satisfying let's say a list of properties. So what are the list of properties? Okay, just very briefly. So if H is a torus, right, because the setting was H is the Levy subgroup of some G. Okay, but one example would be, you know, H could be like the Borel sub. I mean, the parabolic could be a Borel subgroup. H is a torus. Gamma S pi Ri psi agree with, or rather is compatible. Yeah, okay, so agrees with, is compatible with local Langlands correspondence for tori. Because obviously, as the motivation says, we are trying to capture what would have been the local gamma factors for the associated Langlands parameter. But okay, in general, we do not have local Langlands, right? But for tori, you do. So certainly this is a basic thing to check, because if it doesn't agree in the case of tori, then your theory is wrong. Okay? So this says that it agrees with tori. The next property is an important one. It's called multiplicativity. Multiplicativity. Okay. It basically says it's hard to formulate precisely. So let me just tell you the spirit of it. And the spirit of it is, suppose you have pi, and pi is, let's say, contained in, is itself an induced representation. So it's induced from some parabolic Q of H. Then, you see in the setup, just some side remark here, okay? You have G, right? And G has this parabolic. Okay? But now in H, we have another parabolic Q. So of course, so this contains Q dot n, right? So call this Q prime or something. But this Q prime is also a parabolic there, right? Okay, for example. Okay? In fact, it will be a parabolic perhaps of some smaller group of G. In any case, it's at least a parabolic for this group. Okay? So let me say that then this guy can be expressed in terms of Langland-Shahidi gamma factors for tau. So this is an inductive property. It is saying that if your representation pi were induced, then in fact this factor can be understood, can be expressed by some precise formula in terms of analogous gamma factors for the inducing data tau. So as you can see, suppose I want to compute this number, this function, and my pi is not supercuspidal, so it's induced. Then this property, which I didn't write down precisely, will allow you to reduce that computation to the case of supercuspidal representations. And what is the formula? Well, the formula is, I think the best way to think about it is to imagine you have local Langlands correspondence. You go over to the L parameter site. You know if you have some induced like that, let's pretend this is just equal, okay, then the Langlands parameter of this will be expressible in terms of Langlands parameter of that. And then from there, you can work out this relation precisely. Okay, so yeah, okay. So I wanted to state it, but I think that let me not. Okay, I just want to share the spirit of it with you, which is that it's an inductive property. If your pi is induced, you can reduce to understanding for similar gamma factors, but for this inducing data. And the final one is a global functional equation. Okay. So this says that if this pi is a cuspidal automorphic representation of, so assume you are now in a global setting. You have some global field K, you have the adels, okay, so, and which is a globally generic, let's say. Okay, so this theory only works for generic representation. Globally generic, then you have so of course I will put pi. This pi, which is a tensor product of the local components, at almost all places V, pi V is unramified. In particular, pi V is induced from a Borel subgroup. Okay? In that case, we know how to write down the L parameter, okay, for unramified representation. So I have a partial L functions. Okay, so maybe I should have to. I also fix. I fix. Global character of this non-trivial. Here I will put, and then LS. If you substitute this thing into there, you will get what you are used to as a global functional equation or L function. Ls is equal to epsilon times L1 minus S. I should put a check here, sorry. Okay. So, yeah, so Langland-Shahidi theory is to define these guys so that they satisfy some properties, and one of the properties is a global condition. And moreover, and to prove that, in fact, this list of properties characterize these functions, these gamma functions. Moreover, these properties characterizes there's at most one system of functions that satisfy this, and it exists. Okay, some construction is needed to produce this theory. Okay, now of course there are other properties. So for example, right, one thing you might say is that when you apply this functional equation 2 times, meaning here you have Ls equals to something, right? Now you apply this functional equation to this guy, it will bring you back to that, but what you see will be, so of course they satisfy other, they satisfy, let's say, additional properties, which you can deduce from some of these. So for example, you have a so-called local functional equation, which is gamma s pi ri psi, gamma 1 minus s pi check ri psi bar. Equals to 1. Something like that. Okay, so before I break, I wanted to state okay, so as I said, this is the chief application of the globalization theorem to complete the proof or the development of this theory of Langland-Shahidi gamma factors over function fields. Okay, now, so why is the case of function field not proven earlier? Okay, so the reason is as follows, right? So you see, because if you want to construct something that satisfies this list of properties, okay, you already know what it is for tori, okay, because the condition tells you what it is. If it is not supercuspidal, using multiplicativity, you can reduce to supercuspidal case. So the main thing is to produce these things for supercuspidal and to show that there's just a unique way of doing it. Okay? Now, how is that done? Well, that is done by exploiting this global property. Okay? If you have a supercuspidal, then, for example, what Shahidi did in his 1990 paper is to globalize it, right? Globalize this supercuspidal so that at all finite places of the number field is unramified. Archimedean, he doesn't know what you don't know what you get, okay? Because you are using the stringing support argument for Poincare series at that point. Now you don't know what you get, but it's okay because in a Archimedean case, every representation is contained in a principal series induced from Borel. So by multiplicativity and by the first 2 properties, you already know. Okay? You already have this gamma theory of gamma factors. Now, so this means that there's only one place that you don't know, right? And you can use this. So for example, if you have 2 such theories, you can use this globalization and you compare them, and you see that they have to be the same for supercuspidal. So that was how the argument goes. Now, so why doesn't this work for function field? Well, if you try to follow the same strategy and you try to use, you globalize by using this stringing support argument, you always lose control at one place, right? You have to choose one place where you take your support of your test function to be smaller and smaller. Then you lose control of what representation you have there. Okay? But in the function field, you see, every place is equally important as every other place. There's no place where you have prior information. And that's why, that's an obstacle, okay? And that's why this theory was stuck at this point. Okay? But now, in the globalization theorem that we have, we can globalize in such a way that at every other place, it's induced from Borel. Okay? And as a result, the argument can be carried out. Okay? And the argument is the same, essentially the same as in characteristic 0 case once you have this input. So this is the chief application. Okay? But what I want to talk about in the next part is, so I will accept this. This has been done. I'm not going to describe how it is done. I will give you some sketch already but I will, I said here that they satisfy some additional properties. So I want to, the next theorem I want to discuss is a property that this gamma factors satisfy called stability. So I want to discuss how one proves that. Okay, so maybe we can take a break, 5 minutes. This cookie is kind of salty. Yeah, now I'm thirsty. Yeah. Okay. Okay. So let me formulate the theorem I want to prove, because I said here they satisfy some additional properties. So, stability of Langland-Shahidi. So what is it? It's a very simple statement. So if you have, so again in the same setting, okay? So suppose I have two irreducible generic representation of H. So I'm going to index it by F to say, to show that this is a group over F, have the same central character. Then let me write down the statement first and I explain. For all sufficiently ramified characters I of HF, let's say, let me say what this is. So recall that H is a Levy factor of some group G. Let's say G is semi-simple, okay? So because it's a Levy factor, I mean, it will not be semi-simple, right? It will actually have a central torus. In fact, there will be at least a one-dimension split torus in its center, because it is a Levy subgroup. And so there are lots of characters of this group. Right? So in other words, I'm saying that this mod is derived group certainly projects to GM, and there's at least one copy of GM in this. So I can twist. And yes, okay, so I'm saying that if you twist by something which is sufficiently highly ramified, then you cannot distinguish them from each other. That's what it means by stability. Okay. Now, let me say why we should expect this. Again, using the local Langlands correspondence. Suppose you have local Langlands correspondence, so by LLC, right? So each of these pi I, you can attach their Langlands parameters. And recall that we have this Ri, right? So if these parameters are compatible with local Langlands, so suppose that this gamma pi I pi of Ri psi is Ri composed with phi pi. Suppose you know this compatibility, okay? Then this identity will become some stability property for Galois theoretic gamma factors. And in that context, this stability property is a theorem of the Lin and Henya. Okay? Galois theoretic context, stability posed by Berlin and Hania. And that is why we expect the same thing to hold as well. And in fact, the way we prove this theorem, it's going to pass to the Galois side and then use the Lin-Hania. So the theorem, so our theorem will be shown by passing to Galois side and applying Now, of course, if you have local Langlands, then this is immediate consequence. Okay? If you have local Langlands and they show that these gamma factors are compatible with LLC, then it's immediate. So how are we going to pass to the Galois side? Okay? Well, we are going to pass to the Galois side by using a big machine, so to speak, namely the results of Vincent Lafforgue on the global Langlands correspondence over function fields. So I'm going to briefly just list down the results of his that I will use. Okay? And then I'm going to apply these results as a black box. Okay? But in the last lecture of this series on, I think, January 5th, I'm going to come back to discuss Lafforgue's results, just to give you some more details about his work. And so, all right. So basically, what did he do? So basically, L for Vincent Lafforgue. So he defined, or he constructed, a map from say cuspidal automorphic representation of HA. So this is over function field. Okay? K is a global field. Characteristic P bigger than 0. 2, well, it's a global Langlands correspondence. So it's going to here, you are going to go to something. This is the separable closure. Okay, so this is a continuous Galois representation, L-adic Galois representation. Okay, so he defined a map, I mean, of course, with some properties. Okay, so I'm going to list down some of the properties. Okay. Now, let me first say that, yeah, okay, sorry, with L different from T. Okay. T in the now, so of course, when I say continuous, I'm using the L-adic topology on here. Okay. Of course, if you have such a thing, you can restrict to the local Galois groups at any place. You get a continuous L-adic local Galois representation. But again, because the topology here is a L-adic topology, this is not the, I mean, if you're used to the usual statement of local Langlands or Langlands parameters as maps to the complex dual group or L group, there you just don't put any topology at all, right, on the dual group, on the L group. But here we are using the L-adic topology. However, if you are in a local non-Archimedean setting, okay, there is a standard way of passing from these continuous L-adic Galois representations to a representation of the Wedelin group, but without any topological ingredients on the L group side. Okay. Right. Okay. Now, in the function field setting, okay, let me say it. Okay, so I will make use of this passage. In other words, you see, if we fix an isomorphism, you're about to see, then a local rho L V, right? So a priori is a map from the local Galois group to this guy. Okay, can be expressed, can be transformed into into an analogous map, no more, from the Wedelin group. Wedelin group is this thing, right? Of course, it depends on this choice. Okay, which I assume is somehow a more familiar setting for some people. For others, it's the other way around. So, okay, so what are the properties of this map? Well, it's basically that at almost all places where this representation is unramified, you get the expected subtractive parameter for unramified representations. Okay. Just say here.
Excuse me, you must have assumed something on the central character, or you still assume H is semi-simple?
No, so I will come into it. Yes, I'm going to say one of the properties is central character. So are you thinking of more like a finite order central character or something like that?
I think the Galois group should be replaced by global Bay group in order to formulate it correctly. Because the power of flow is.
Yes, okay, I understand what you mean. Yeah. So put the whatever compactness condition you need for to have this. Yes.
Finite order than
yes, that's right. Yes. I guess I need the central characters to be something like L-adic units or something like that. Mm-hmm. Right. Yeah. Okay. So didn't check this carefully. So this map satisfies. So firstly, as I said, for almost all V, yeah, so I didn't finish my thought here. So by some standard process, we can convert a continuous L-adic local representation to something like this, with the usual Langlands. However, in the definition of Langlands parameter, there's usually a condition that the Frobenius element is mapped to a semi-simple element. When you do this translation, this may not be satisfied, okay? But there's another standard procedure where you Frobenius semi-simplify this representation. What does it mean? It means that when you take the image of a Frobenius, suppose it's not semi-simple. That means that it has a Jordan decomposition. You can write it as semi-simple times unipotent. Now, throw away the unipotent and define a new representation that sends a Frobenius to that S. Then you have to check well-defined and so on, blah, 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 and you get something like that. Okay. So this will be, now in the context, this will be a usual L parameter. I was explaining this just because I want to say that, well, at almost all places, I have pi v is unramified. So you already know how to define Langlands parameter for unramified representation. It will be something like that. Now, on the other hand, on this side, for those v, I will have a rho LV. By this process, I'm going to produce something which is a usual Langlands parameter. So now I can compare them. Okay. So let me just say rho LV gives the L parameter, which is a Sadaki parameter of pi v. Okay, so L was, which is a pi, where I'm looking at a place where pi v is unramified. So this just says that at the unramified place, you get the expected thing. Okay. Now, the other thing I want to say is about central character. So if you look at the connected center of HF, then on the dual side, you are going to get a map rho z from L. So firstly, you look at this. This is say a complex group. So you can, of course, project to the connected part, and which is the dual group. Okay, and then you take a derived group. Okay, then this quotient is actually just the L group of Z. Okay, so now, so the second property is that then the central character omega pi of pi. If so, you have a central character. Of course, this is a torus, so we have local Langlands for global Langlands for torus. So it's going to give you a map from the vague, so say some Galois group to this thing. Okay. The central character corresponds to rho z composed with rho pi. So if I have pi, and so Lafforgue defined this map, I get an associated rho pi. Okay, rho pi is a map from the Galois group to this thing, right? So when I compose it with this projection, right? So this thing is now from the Galois group to the L group of a torus. Okay. Now, I want that parameter to agree with the central character of pi. Now, of course, this is not this property. You can inherit. I mean, you can deduce it from property A, because you know already that at almost all places, things matches up. Okay, pi v corresponds to the local rho v, just give the L parameter of pi v. So of course, on the central character, they will also match up. So you already know that these two guys match up almost everywhere. So by Chebotarev density, you deduce that they match up everywhere. So the central character itself has a global Langlands parameter by the global Langlands correspondence for tori. That is also a map from, say, some vague group to this thing. But now I have this rho composed with this projection. That's another map. And these two maps we already know agree at almost all places. Okay, so they agree at all places by Chebotarev. All right, so so as I said, I'm going to take this result as a black box. Okay? I'm going to use it to prove this stability by passing to the Galois side. And I hope the argument will illustrate for you the nature of global to local argument. Okay, so proof of stability. Okay, so the main thing is to prove the following lemma. suppose you give me any irreducible generic representation of HF, then I want to find there exists a local L parameter phi from the Beta-Lin group to the L group such that so two conditions hold. The first is that I want the central character of pi to correspond to rho z composed with phi under the local Langlands correspondence for tori. Okay, so this means I know I don't want to lose control of central character. Okay, and the second one is I would like this this to be equal to Ri composed. Suppose I have this, then I'm done. Then, because then I can apply the Lin and Henya. Right? So because so given the lemma, okay, so if pi 1, pi 2 have same central character, then according to the lemma, I have some parameter phi 1 and phi 2 that satisfy this property. Right? Okay, so maybe so let me. I want this, sorry, not just for this, but also twisted by any chi, I guess. I mean, for all characters, chi, okay, of M, let's say, not M, H, I guess. Okay, so the lemma produce for me phi 1, phi 2, right? Moreover, rho z phi 1, well, rho z phi 1 is correspond to this one, but this is the same as that. Okay, that's the assumption. So, and this correspond to this. Okay, so in other words, it means that rho z composed with phi 1 is equal to rho z composed with phi 2. So this means that for any representation R of LHF to LB, determinant of phi 1, sorry, R composed with phi 1 is the same as determinant of R composed with phi 2. Why? Because if I take determinant, now this is surely going to factor through the derived group of the identity component. It's going to factor through so let's just write the dual group derived. Okay, because the derived group is going to be some complex simple group. I mean, the derived group is the commutator. Okay. Right. So if I, and of course this is my rho z. Okay. So if I have phi, and I look at R and I compute determinant, it factors through phi composed with rho z. So since those two are equal, I get this. So this is necessary just because I need to, I want to apply the Lin and Henya, right? Okay. And now I can apply it because if I take a sufficiently highly ramified chi, then the gamma of pi 1 tensor chi will be equal to this Galois theoretic one. phi 1, and similarly for pi 2. So those two Langland-Shahidi gamma factor will be equal to the corresponding Galois theoretic ones. Now, and they have this determinant condition holds, so I can apply the linear Hannian to show that if the chi is sufficiently ramified, they are equal. So the point is to prove this lemma. And as you might guess, we're going to use Lafforgue's theorem to extract out this local guy, and the argument will be something like this: you get pi, okay? You globalize it using a globalization theorem that we have. Then, so now you have a cuspidal representation. You apply Vincent Lafforgue's map to get a global Galois representation. Okay. Then you are going to take the corresponding local Galois representation at the place that where you have your representation pi. But you want to do it in such a way that the conditions in the lemma hold. You have this and okay. So first, the proof of lemma. Let me just say you can reduce to supercuspidal case simply by using this property of multiplicativity. If pi is not supercuspidal, is induced on something, and you can express this in terms of analogous Langland-Shahidi gamma factors for the inducing data. And let's say the inducing data is supercuspidal, and you already know how to do that, say by induction on the group, something, then you can get some parameter, of course mapping to the L group of that levy. But the L group of levy then maps to this one, so you will be okay. So basically you reduce to supercuspidal case. Okay. So now, how do you do it in the supercuspidal case? So you apply this globalization. Theorem, and you are going to get, or rather the corollary, okay. Okay, because in this case we only have local data, so we have to globalize the field and everything. So you are going to globalize, so initially you have this setting, right? Parabolics and blah blah blah. You have pi. So you will find some, you have this, you will find some global field. Okay, well this is still quasi-split. Okay, and this is globally generic. That's what our corollary will give us. And moreover, globally generic, and of course, this pi is such that at all places outside of V0, so K V0 is F. Outside of V0, this pi V is in principal series. It's contained in principal series, used from Borel subgroup. Right? Now, you apply Vincent Lafforgue construction. So this pi will give me a rho pi. Okay. And so let S be a large enough finite set of places such that for all V not in S, everything is unramified. Okay, so HV, pi V, and so on are unramified. And right, and this rho pi V is the L parameter was the property of basically the only property I state of this Vincent Lafforgue's map. Right? Almost everywhere it is the right thing. Okay? So I fix some set S such as outside of this, it is the right thing. Okay, now I'm going to apply the global functional equation. Oh, okay, no. First, I also want to globalize chi. Okay, so I globalize because I have some chi in my highly ramified chi, right? No, this chi is for all chi. So I have some chi, and I want to show this. I want to show this for all chi. So I take an arbitrary chi, globalize chi to bigger one. So at the moment, let it be an arbitrary one. Okay? Let it be arbitrary. But later, I'm going to use some more properties. Okay? For example, here I say, I'm going to assume this S is disjoint from V0. Okay? So one of the properties I'm going to put later on is that at places in S, I want this to be highly ramified. Okay? And I think just now at the beginning when I proved that globalization of character, I mentioned that I can do that. Okay? So at the moment, let's take it to be, just take some globalization. All right. Okay, so now the next part is apply global functional equations. Okay, there are two global functional equations. Okay, one of them is from Langland-Shahidi theory. Right, that was one of the properties of the Langland-Shahidi gamma factors. There will be some product of V in S. Sorry, there will be some twist by this chi. Okay, so I'm going to write R for Ri. I mean, I forgot to say that I will fix some. This, then must be an R here. So this is the global functional equation for Langland-Shahidi theory that I recall in the first hour that I have discussed. Okay, but on the other hand, there is a functional equation for the L function associated to this global Galois representation rho pi. Okay? Now this is a feature of function fields because of course in number field if you have a global Galois representations, for example the action of the Galois group on the Tate module or elliptic curve, you a priori don't know how to prove continuation of this guy. Okay? But in function field, there was of course this is a theory of Grothendieck that this global Galois representation has firstly it's a rational function, then it actually has a functional equation. Okay? So you will get something like this: R composed with rho pi chi okay, is equal to okay. So I forgot this V naught. The local these two global functional equations. Now, because of the property, or this property, the definition of S, outside of S, this and this are equal. Similarly, this and this are equal. Okay, I should also say, so therefore, and also chi v is also unreplicated. I have fixed, have I fixed it? I don't even know. I have not, but I should. Maybe I should, sorry, I should do this global, this with here. Then this. Now, okay, so I know that these two, this is equal to this partial function is equal to this partial function. So I'm going to conclude that this finite product or gamma factor is equal to this one. I will deduce that this will stand for Langland-Shahidi gamma factors, and this is the Galois theoretic one. I'll get this. Now, okay. Now let's look at this this side. Okay, I have of course the place I care about. Right? And I have these other guys, but this other guy, the representation is induced, is a principal series induced from Borel. So by the multiplicativity of, so for all V in S, gamma, I mean the V, right? This thing, yeah. So let me say, so because pi V is induced from Borel, by multiplicativity, I can write this in terms of gamma factor for torus. Okay? Then another property of this LS gamma factor is that for tori is compatible with local Langlands for tori. So then I can express this in terms of Galois theoretic L parameters. Okay? So the L parameter will factor through the L group of the torus inside the L group. So let me say by multiplicativity. So this is one of the properties of Langland-Shahidi theory plus compatibility with LLC of tori, and using the fact that pi v is a principal series. This thing tells me that for all V in S, gamma LS V can be written as the Galois one for some, so I'm going to write it out here, for some parameter, something, okay, I don't know what it is, but it's something. So now, if you look at this identity, you see that there's only one term which has a gamma LS, which is a term at V0. So everything is now gamma Galois. Okay? So you bring everything to the other side. So you see that gamma LS at V0, this is the one that you care about, is equal to well, you have the gamma Galois at V0, okay? But then for all the V in S, you will have something like this, okay? Where it will look something like this. So the top is a rho pi V tensor chi V, and here you will have R composed with this. Who knows what these 5 V's are? the thing inside here is the same as the numerator. All right, but now if you choose, if for all v in S, okay, and also, I mean, the central character, I mean, the determinant of this and determinant of that are the same. Okay, determinant of this and determinant of that are the same. You can check it. Then, if for all these things, chi v is highly ramified, then the Lin and Hanyard, so the Lin and Hanyard said that if this chi v are highly ramified, the top and bottom will look the same, will be equal, so they will cancel. Okay. This product is equal to 1. Right. So the point is that this identity holds for any chi, right? For any chi that globalize your given one. So you have this identity for all chi. Now, in particular, you can make. So now you can apply it to a global chi, which is sufficiently highly ramified, depending on these two guys. And you make it 1, and then this proves so this implies your lemma. But once this is 1, then you have these two the same, and then you are done. Okay. And let me just finish with a corollary. Corollary of the proof of the lemma is that now if you give me any cuspidal representation of some global group, you give me any Tecker character, okay, then and you have this additive one. Then for all v, okay, no, and so let's say pi, give by Lafforgue something, then I guess what I want to say here is that for all v, the gamma factor matches up. This can be, I mean, this is this consequence of the proof, or the proof of the lemma. Right. So you have this sort of compatibility of Lafforgue's construction with this shows that this Langland-Shahidi, because this side is Langland-Shahidi, this side is Galois theoretic. It's compatible with the localization in Lafforgue's construction. Okay, so what I want to talk about next time is actually, I have planned for one other thing, very short, which is that, so as I said, Langland-Shahidi deals only with generic representations. What if the representation pi on the levy is not generic? Well, then there's no such theory. But there is a even coarser invariant that you can consider, coarser than the Langland-Shahidi gamma factor. And what is that? That is the so-called punctual measure or punctual density, okay? Which is, anyhow, maybe I will start with that next time. It's just very short. So why is it coarser? It is because if pi were generic, then this punctual measure can be expressed as a product of this Langland-Shahidi gamma factor for the Ri's. Okay, so, yeah, okay, so it is coarser in that sense. And so for non-generic representation, you can nevertheless consider this coarser invariant, okay, because it makes sense for every representation, not just the generic ones. And you can prove a similar stability result for this punctual measure, namely if you have two representations, pi 1, pi 2, with the same central character, then for sufficiently highly ramified twists, the punctual measure becomes the same. And then you can prove the analog of this for punctual measure, which is that you have some global cuspidal representation. You look at Lafforgue's Galois representation. Then you have this equality of invariance, where instead of gamma functions, you look at this punctual measure. This is also proved in the same, using the same sort of globalization argument. Okay. But of course, you see, when you prove a local result from global, what happens is you have one place where you are trying to prove the local theorem. Of course, you have to globalize in such a way. In this globalization, you must make sure that you understand that local theorem already at all other places. Okay? But even then, you see that's not enough in the sense that suppose that the local ingredients are all independent of each other. Then clearly, there's no reason why you can deduce something at V0 from what is happening elsewhere, right? However, in the globalization, there's one extra condition, the condition of being automorphic or being a global Galois representation. That's an extra condition, and this is a condition, this condition is the glue that stick these local places together, right? And in this argument, what is this glue? Is this global functional equation, right? This is saying that, because a good way of thinking about this global functional equation is to say that it is basically saying that the product of all gamma factor is 1. Of course, this product doesn't make sense, okay? But this is a good way to think about it. Is this local invariance, and product is 1. So this equation is the glue that relates, showing that these places, these local things are not independent of each other. Right? So now imagine you understand gamma V at all V except at one place. Then this equation will allow you to deduce what it is at the remaining place. Okay? So in the case of punctual measure, what is the analog of this glue? Well, it's some global functional equation too. And that basically is the global functional equation for global intertwining operators. So that's okay. So what I think next time what I want to talk about is to sharpen this result. See, because it's very tempting now that you have this Lafforgue construction, you can try to use it to deduce a local Langlands correspondence, right? You globalize, you look at the global Galois representation, you pick out the local component. But now you have to ask yourself, is this well defined? Because you could have many ways of globalizing, and do you end up with the same thing? So that's what I will talk about next time. Thank you.
Questions, comments?
I'm going to talk about the local analog of Lafforgue's map, meaning starting from all representations, user representation of group over local view, constructing a Langlands parameter. And then this map should satisfy a bunch of properties, namely one of the properties would be something like this, that it is the Langland-Shahidi gamma factor is compatible with the Galois theoretic ones. And also, this punctual measure that I didn't talk about, also compatible in some sense. And then I will show that these properties uniquely determine this map. There's at most one map